it's working. Let me know in the chat if it's not, or on WhatsApp or on Discord, whichever way you can contact me. Seems like my bitrate is not good. Just a moment. How do I change my stream bitrate? Stream health. It's good. Settings. Enable auto start. I should have. Enable auto stop. I should have. Okay, cool. Seems like I'm here. I think I just got a like. I think that's cool. Where do I put the chat? I want to make the chat go. Pop out the chat. Pop out chat. So I can probably close that window, and we are here. Okay, cool. So let's think about this. What do I want to do today? My objective today is I've got this PR in the Zephyr project, which is to this one. I've got this PR in the Zephyr project, which adds drivers for the NXP SC18IS606 I2C SPI bridge. So this is what I'm adding drivers for. Sorry, there's a screen on the side, and whenever something opens there, I have to look. So I'm adding drivers for this bridge. What this bridge does is it enables you to build a bridge from I2C on your controller or on your computer, and then it enables you to basically expand it into either two options. It enables you to expand it into either a GPIO port, so you can go from I2C and you can get 4 GPIOs, I think 3 GPIOs if I'm not wrong, so SS0, SS1, SS2, and those SS0, SS1, SS1, SS2 are basically, in old terms, they're called slave select, and in SPI we use that for addressing, because SPI does not have an inbuilt. I mean, if you go down in my streams enough, you'll find that. By the way, the links to all of the things I'm touching about will be in the description later, but if you want the link to the pull request, it's already in the description. You can go to that, and then you can kind of use that to build up to everything. But yeah, so the point today is, can you guys hear me? I don't know, if someone can hear me, please say it on the chat. So what I'm trying to do today is add a feature to my driver where I can handle both situations. And by both situations, what do I mean? I mean, I need to be able to choose which controller I want to use. So am I using the I2C to GPIO, or am I using I2C to SPI? So because this is a bridge, and what I don't want to happen is for an SPI transaction to be going on, and then for someone to be using or wanting to use one of the GPIO pins. So I want to separate them. And one of the easiest ways to do this is using Mutexes in Zephyr. So let's check out Mutexes in Zephyr. Zephyr Mutex. Zephyr Mutex. So Zephyr has Mutexes, and Mutexes basically enable you to lock something. And then you have a number of people. You can count the number of people who are waiting for something or a resource, and then you can lock it. You can basically, when you're consuming the resource, or when something is consuming the resource, it can lock that resource. And then basically, as once you lock the resource, no one else can use the resource. So the design we're going for here is that SPI can lock the bridge, or GPIO can lock the bridge. So that way, whenever there's someone using a GPIO pin, you don't have the chance of SPI coming and interrupting the GPIO work. Or if there's someone who's using the SPI pin, you do not have the chance of someone SPI bus, basically, because SPI is 4 pins. You don't have the opportunity of an application coming in and grabbing the GPIO pin and thereby interrupting what you're doing. So I have a fairly I2C Yeah, I do have an implemented the SPI version of this bridge. The I2C to SPI version of this bridge is implemented, and this is the one that is on the link in the description. This is the draft pull request. So what I want to do is I want to modify this driver so that I can add a mutex to it. And if I can add a mutex to it, I can control who is controlling the I2C bridge, I2C to the bridge. Let's just call it the bridge to make it simple. So I can see who's controlling the bridge, and I can allow control to continue until it's done, and then someone else can take it, or someone else can take it, or I can hold it until I'm done. So this is in the perspective of the bridge. So one of the easiest ways of doing this, as I've gone through the Zephyr code, and I happen to know that there is someone else who had encountered the same situation, and I think it's Zephyr. I think it's an SC704, SC1, yeah, this one. I want to find you, SC18. I am 704. Okay, cool. So this is a driver for the it's the same sort of driver. Let me just quickly pull it up so that we can see it, and then we can move on to something else. So this is the same sort of driver. It's a UART to I2C bridge. So now this one is different because mine expands from I2C to SPI, and this one expands expands from UART. So two lines into it looks like 8 GPIOs. So this has already been implemented in Zephyr, and they basically went through the same problem I'm going through, which is determining who owns a bridge and who is going to use the bridge at the time. So what I'm going to do is look at their implementation, which is look at their implementation, see what I can learn from it, and then see what I can carry over into my implementation. And specifically today, we're just going to be looking at the Mutex only, or rather I'll just implement the Mutex on top of the SPI part that I've done, and then I'll do the GPIO implementation offline, or I could do another stream later if anyone is keen for it. Just a break, let me check if anyone's complaining. Yeah, cool. All's good. So let's jump on. Let's see what we need to do here. So let's look at this, and then let's go and look at the header, and then here we can see what actually we want to see. So you can see there's a couple of functions. There's a claim function, there's a release function, and there's a transfer function. So let's look at through the documentations of this all. So claim function, after this routine, the device cannot be used by any thread until the release routine is called. Cool. And then what parameter does this take? This takes the actual device. So this takes the bridge itself, and then it returns either 0 for success, that you have a lock on the device, or it returns busy, which means you cannot claim the device, someone else has locked it right now, so you have to either do a busy wait to something or do some work and come back later and see. or you can, I don't know if in Zephyr you can ask the Mutex to tell you when it's done. We'll check that later. And then we have a release routine, and release routine basically this it lets go of the claim that you have, one has, and a device has, or a thread has on this actual on the bridge. So the release routine lets go of it. And then the other for this code, they've gone as far as making all the transfers in one. And what do I mean by that? So when you have an I2C to SPI bridge, or a UART to I2C bridge, what you're doing is you're basically sending I2C messages, and you're depending on the bridge to convert those I2C messages into SPI messages. And if you go through if one goes through the data sheet of all of this, which I won't because it's going to be becoming deep and I want to focus on mutexes, you will see that you basically write into a buffer, and then the device will copy from the buffer into SPI, or you ask the device to read, and then once it reads, you can read from the buffer. Yeah, and that's really what happens. So in I2C, you have we could also end up implementing a transfer function. That way we have all our transfer in one place, so that you can either read or write from just one function. But that goes beyond the implementation here, and that could be a later stream. So that could be modifying my driver so that it just has one transfer call. My initial idea was to just have either a write or a read, and it's just two functions. It's one more than these three, which makes it almost trivial to run. So at the moment I'll go with the simpler option, which is having the both. So let's start doing this, and then we can later what we'll do is we'll be able to go into the code of this, and we'll look at the code of this. Is really simple. Like it really, the code itself is probably 4 or 5 lines. So let's look at them. The meat of the work is done either in the library implementing the mutex itself, or in understanding the concepts that are concerned with this. So let me, shame, just did that to myself. So let's open that. I don't even know why I'm doing this on the browser, because I have all this code locally, but you guys can see better on the browser, I guess, or that's what I think. So let's look at that. Come on. SCI, S is going to be lower, S is going to be lower, higher than R, or RS, lower than S, lower than R, I2C. Why can I not find what I'm looking for right now? Yeah, so here. So let's open that, and let's look at the claim. So you can see the claim is just 4 lines, the release is just 4 lines, and then the transfer is actually the meat of the thing itself. But the transfer function isn't really what we wanted. We just want to know where it's locked and where it's released, really. So let's go ahead and implement this, and then see what we need to do. So the first thing we need to do is to enable ourselves to have a, how do I call this? We need a mutex. We need a mutex that we can actually lock or release. So if we look at Zephyr Mutexes, Zephyr has mutexes. Yeah, so Zephyr has a struct Mutex. Okay. So it has a type called Mutex, which is a mutex. So let's add a mutex into our driver, and then we can start using that. So Let's go and do struct Mutex. Mutex. So let's call this bridge block. Perfect. And okay, so that's number one. The other part is we need to add a header for this file. So we're going to do SPI and NXP SC18IS606.h. So let's build a header for this file. And I'm currently sort of unaware. I don't know why people, or rather why it's necessary to do the extant C in headers. Maybe someone who knows about C++ and possibly Marvin, I don't know if you're here. If you know about C++ and you know why we need why we need to do extant Cs in our Zephyr headers, that would be cool if you let me know. But I think it's so that if anyone is using C++, yeah, and then we can do that. No. If def C++ extant C, let's make a thing and then do that, and then this should be a macro, a definition. So then and I think at the end of this all, what we need to do is also to end this, we need to end it with the same thing, isn't it? Yeah. If def C++, why am I typing things when I don't need to? So then here we can do that, and then here we can do hash. Yeah. So now let's go in and implement our coding here, or rather our function headers. So the first thing we need to do is add API declaration for the claim. Okay. So let's do int NXP SC18IS606 claim. Okay, there's that. And then this takes a struct. Let's make it a const. Construct device. So it takes a pointer to the struct. Yeah. And then let's add some documentation here so that we are actually responsible open source developers, because we want people to be able to use this code. Okay, so we'll do a brief claim the SC18IS606 bridge. Okay, and then let's add a warning. After calling this routine in the device not be used by any other thread and until the calling bridge releases it with the counter part be around me. Okay, and then add param dev, which is an SC1 I8 IS SC18 no SCI8 SC18 so there's no IS606 device. That's what it takes. And then at redval, let's say it returns 0 device is claimed. At redval busy means the device cannot be claimed. Okay. Let's now also add a counterpart to this function. Okay, so let's add. So first of all, we'll do that, and then we can even so what? Anyways, so let's do another brief here. Release the SC18IS606 bridge. I don't know what this will take. This will also take the device itself. So you need, in order to call the release, you already have to have called the lock. So let's warning. You can on this routine can only be called once our device has been locked. Okay, and then let's say add param is the device SC18IS606 bridge, and then it has a few red vals, this one, so I'll just write them down because you can always find them. At red val 0, the device is released. Okay, at red val epalm just means the current thread has not claimed this, so cannot release it. Okay, and then at red val inval is the device has no locks on it. Okay, cool. So, and then we do that, and then we have that, and then we have an integer, and then we have an NXP SC18IS606 release. Construct device dev. So for now I leave it at this two, because really today what we want to focus on is just the mutexes, you know. So I can leave it at this two, and then I can go offline and basically how do I say this? I can go offline and basically implement I can go offline and I can add the transfer functions to here. But I'm wondering, why do I have this? Yeah, that's fine. It should almost be ready. So if I do PF C18IS. Yeah, we have a header and a thing. So first of all, I need to include the why is my buffer still showing the error? Spacey. I should probably add this to okay, cool, sorry about that. Why is there a release function in here? What is happening? Oh, I know. It's not this is SPI function. Fine. SPI release. So this should be called here SPI release. SPI. Oh yeah, I need to follow my own naming conventions better. So let's do that. SPI release, and then we can come here and be like SPI release. Okay, and then now we need to go and include our own. We need to go and include our own header, and I think include. So it's going to be NXP. Yeah. SPI, NXP. Okay. Okay, so let's include that header, and then let's go down and sorry. So include, and then I'll say SPI NXP. Okay, cool. So there's that, and then we needed to. Did we add our mutex? Let's add our mutex. I think I messed it up for some reason, and I would like to. Yeah, I think. It's fine. I'll leave it at that. There's a problem that will come back later, but we will do that. We will. Okay, Mutex. Okay, Mutex. Is it? Is it a K Mutex? Is it a K Mutex? Is a struct a K underscore Mutex, or I'm looking at the docs? Yeah, and I I see. Yeah, this should probably be the fast one because in the end it's gonna affect us. So let's do a struct. Okay, let's go mutex bridge. Okay. And then we need to implement SC18IS. Okay, so that I can move through these functions easy. This file's easy. So now we need to implement. Yeah, let's look at what we want to implement claim, and then we'll implement release. So if we want to implement claim, I can even copy this. Why not? I can probably do. So let's put this. So let's implement this function here. So let's implement the NXP SC18 claim. Yeah. So what will this do? We will take. We have the mutex that is in the. So first of all, we need to get the device data. Okay. So if we have the device data, so let's go struct. How am I getting the device data? How can I forget this already? Yeah. Anyways, struct NXP and data is equal data is equals device, and then in the device we will get data. The data fit. So we have that, and then from here we will do return. It's that simple. K mutex lock, and then this lock takes this K mutex lock takes a mutex. So in I think in data we have a bridge lock. Yeah. That's really it. And then for how long? Forever. Okay. And that's that function. That is the implementation of our claim. So this grabs the device. You know, I want this device, lock it until I'm done with it. Cool. And then let's go back and let's save that. I wanna, yeah, sorry. Let's save that, and then let's go back, and then let's go, I know it's something like YY, but I don't know why, no. And then let's go back and implement release. Okay, so in release, what we want to happen, we want to go like when this routine is called, we want what to happen. We want it to basically this is if I remember well, this is a Zephyr convention, and it's gonna come later in reviews. I'm gonna be told to do that, so let me do it now. So in release, we want to do the opposite of what we did before. So struct, let's go into the device, NXP, and then that's the data. Let's give me a pointer to the data, and then in the device, I want the data fill, and then that's nice. and then I want to return k mutex release or unlock. Is it unlock? K mutex unlock, and then in here I want to go give me data. In data, give me the mutex at 1. Boom, shakalaka. So really, this really, to be honest, this is our implementation. So number one, Zephyr, our operating system, gives us mutexes. Let me see if anyone is asking any questions before I go on. Zephyr, our operating system, is giving us mutexes, and it enables us to lock and unlock those mutexes, and then it also enables us to, how do I say that? It enables us to lock and unlock those mutexes, and then as well as that, it enables it. So most of the work is really done for us. The mutex is there, you can just take it, and it'll do the switching by itself. And this is how we're going to be using this. In here, I will, before I write to a register, before I go to write to, because in order to operate this device, you need to send it I2C commands. There's only one way to talk to this device as the controller of the device. You send I2C device to it, and sometimes you need to read from it. And most of the times, actually, to be honest, even when you're reading from it, the way this device operates, the way SPI operates, because SPI is a master controlled bus, you never actually, there is no read function. What you do is you write a read function, and then the SPI slave or being controlled element on the other side spits back, how do I say this? Spits back the data, but the only way to read SPI devices is usually to write to them, and then it will give you back the data. So, and what we want to do here is NXP. So NXP, let's claim the device, and then in here we will take stop. I'm not gonna do that here because this is write register. I want to do it somewhere else, not in configure, not in transceive. Do I want to do it in transceive really? Because transceive itself is I have to implement a higher layer that in itself is going to be used by transceive. Here's the reason, because transceive is how you implement the SPI part of my bridge, and by implementing it here, if I lock it here, I would always assume that it's the SPI work that is going on. So let's go one layer above. This device is an I2C to SPI or an I2C to a GPIO bridge. Whenever you are operating the device, you need to either be doing a SPI transaction or a GPIO transaction. In SPI transaction, you're writing to the thing or reading from the thing. Okay, and then in a GPIO transaction, you're either writing to the thing or you're reading from the thing. If a GPIO is an input, you're reading from the GPIO. If your GPIO is an output, you're writing to that thing. So we need to basically introduce a layer that abstracts away the how do I say it? abstracts away the, I've forgotten the word of what I want to say. It abstracts away the communication, the particular communication, whether this particular thing is SPI or GPIO. We need to add a new layer that doesn't care which one it is. This new layer is I2C. It already exists. It's just we need to move some stuff into it. Whenever we're doing an I2C transaction, we need to go like, whoever the thread that wants to do this I2C transaction needs to be owning this device, and then the thread that is not doing this, the thread that is, so it's either the I2C thread, or it's either the SPI thread or the GPIO thread. What happens there is that whenever there's an I2C transaction going on, the device won't be allowed. You won't be able to suddenly use GPIO transactions in the middle of SPI transactions, which means thereby you're protecting the pins. You're not going to break the pins. So you're not going to basically grab an SPI slave select pin and just be like, oh, okay, cool, let me use it while an SPI transaction is going on. And for that to happen, I need to change my driver so that there's a middle layer. Right now, the way I've done it is I have an SPI layer and I'm going to have a GPIO layer. That's fine. But right now, I've done quite a bit of my computation. If you can see here, let's look at it. So as you can see, inside my SPI driver, I do I2C writes and I do I2C reads. And what I don't want to do, so do I ever use that function? Reg write and reg read. I found a bug in my code. Cool. So I need to, write reg, and I need to implement another, so it's here. And I need to implement a static int SC18IS606 read reg. Okay, and then this should always take a device. This should also take a device. Construct this should take a device, and the data that you int a t reg, and then you int 8 t volume. Cool. So this is, I'm going to go back. I have to go through my code and implement this so that wherever there's so let's do 2D. Wherever it's happening, wherever I'm doing either a write or a read below, I need to be able to, I should use these functions rather than, as you can see in my transceive itself, I'm actually doing straight I2C, where is it? In my transceive function, I'm calling I2C writes and reads. And I'm using this device. And where is this I2C device? Where am I getting that I2C device? Yeah, you see. So it's inside the device. Boom. So I need to move this so that it's happening in a different function. And then in those two functions, in my two functions, I will be able to lock and unlock the devices. And once I lock and unlock the devices there, this code can just go on as it can basically, this code does not need to know that was added. And it just needs a bit of a redesign. Anyways, in any case, let's do a little recap. Let's actually save this, Shift-T, and then let's do git diff. Let's go into Zephyr. So our code is on Zephyr itself. Git diff. So what we have done is we made what is it that we made? The first thing that we made is we added okay, no, git status, let's see. Okay, git add drivers. Okay, git diff, git diff dash staged. Okay, so let's look at it. So what we did, number one, is we have a net new header, and this new header is going to be shared between our SPI, our SPI functionality and our GPIO functionality. And in our net new header, we have declared a claim and a release function. And this claim and release function uses mutexes to lock the bridge, so that when either SPI is using the bridge, GPIO cannot take it. When GPIO is using the bridge, SPI cannot take it. That's what we've done. And then we've gone further, and in our, since we're using our SPI, since our SPI part was the one I implemented first, you can do this in GPIO as well, whichever side you decide. In here, we've declared these functions that we will be able to use on the other side as well, basically. And in here, we've declared these functions so that they basically enable you to claim or release the device. And then now the next step is going to be to add implementations of write register and read register that allow one to claim and lock this device. Once we add those implementations, then we can use those implementations in the SPI part and in the I2C, in the GPIO part. I think I've mentioned a lot of alphabet soup today, and I think that is really sufficient. It's been a very interesting one. As it turns out, Mutexes are surprisingly simple and straightforward, and yeah, nice to have everyone here. Let me see if there's any questions on the chat. We'll start by checking if there's any questions on the chat, and then we'll see. Redro. Ooh. Thanks, Brian. Let me see. Brian says I should use Redro. Thanks, Brian. No, I didn't know that one. I usually use something like LSP update, LSP restart. I usually use something like that, and then that ends up removing the error. But nice. Now I know a new git. What the fuck? Sorry, I'm swearing. I know a new Vim incantation now. So let's do this. We've added that. Git add, git commit dash n. Let's do a dash v because it's a lot. So in here, let's go drivers SPI, add a mutex to NXP SC18IS606 to share between SPI and GPIO. Added header for the API of the NXP SC18IS606 driver. Implemented the lock and release functions for the driver between GPIO and SPI. Okay, cool. Let's do that. No, you're not in Vim. This is Nano. Rolex. Yes. Git push I2C. I see. Perfect. And then if we go back here, we shall see. Let us refresh. And if we go down here, what will we find? We will find that perfect. We'll find a new commit. It's up. It's running. So, thank you all so much. That was an interesting hour. Mutexes are surprisingly simple. Very basic tools that you can use very straightforwardly, but you have to understand quite a bit before you want to use them or try and use them. And I have some to-dos in my code. Now, thank you so much for hanging out with me today. I'll see if I can do another one soon, and I'll see what new interesting problem I find in order to do that. Maybe I'll do the GPIO implementation as a stream, but that might be a longer stream because you have to look up a lot of stuff, and I don't know the GPIO API offhand, so I have to look it up while I'm doing it, and I have to like copy stuff and stuff. So we'll see on what can be done, but thank you so much for hanging out today. That was cool. Really like it. If you have any suggestions, ask. Cheers. Thank you. It was cool. There's 3 minutes if anyone wants to ask questions. I'll check the bash. Yeah. Only Brian is keen to come for my things. Odd enough. Cool. Cheers. Thank you all so much. Amazing. OBI.